no one is here, I mean, except our people. Shall we wait for a couple of minutes?
Okay, sir.
Yeah. All right, guys, I think, yeah, I see a couple of students. Let's get started. Can you start the live stream, please? Okay, let's do this. So, first of all, welcome everyone for this live session. It's my pleasure to interact with you guys. And I didn't get sufficient opportunity to actually do this before somehow. Well, okay. So yeah, so for some of the other reasons, I think we have been delaying it. And now onwards, I'll make sure that for the next couple of weeks, we'll meet you every week. And so, yeah, let's start with any questions that you have. You can feel free to introduce yourself and say, what is the question you have, and I'll be happy to answer. Any questions? Vinod, I think you are mentioning that there are some questions, right, in assignment 8?
In assignment 8, question number 5, sir. It's asked by Ghosh. Samba Ghosh.
Okay. Okay.
He's here only.
Yeah, he's here.
Yeah.
So I'm sorry, unfortunately, I don't have the assignment 8. Do you have it? Can you quickly share it with me if you can?
Sure, sir.
Or assignment 8. Or let me look up 1 second. QP week 8. Okay, week 8 was, I think, good. Sambha Ghosh, you are there? What was the question? I'm seeing the questions. I think which part was the question? Where was the question problem? Which problem?
Sir, Saurabh shared it on WhatsApp. You can check. Yeah.
I also opened it now.
Okay.
Okay, so, yeah, I opened it. So what problem? What was the question, Vinod? There's a concern. Oh, this is
No, you just mentioned the question numbers. That's all. I
question
don't
number
know.
is what?
5 and 8.
5 and 8. Okay. Let me try to. It's opening. Okay. So first of all, the initial thing. Okay, we started with this, and then this. Question number 5. In curve C, we do not observe any oscillations in the probability of finding an atom in the excited state. This is because, okay. So now the question is, Ghosh, I mean, are you there? Can you hear me? Okay. So the idea is, what is this? Okay. Yeah. Thank you. So what are we talking about? Okay. Here, what is Rabi oscillation? Correct. Generally, when the assignment was nicely done in some way. So if you take initially, there are number of atoms 100 here. Initially, there are 0 atoms in the lower state. Okay. What do you expect? You expect that the atoms in the excited state will de-excite, right, by emitting a photon. Okay. If this energy is E1, this energy is E2, they will emit a photon of energy E2 minus E1, and then they will come down, correct? This is the idea. So after some time, let's say there is a certain time associated with it. We call it, let's say, tau recombination. Okay, tau, radiative lifetime. Okay, radiative lifetime. Okay, what we are saying is, let's say this is the initial system, N2 at 0 is 100. Okay, and if I look at this at N2 at T much greater than tau R, what will be N2? Yeah. Ghosh? What do you think will happen here? Or anyone else? What do you think will happen?
It will just take a equilibrium state. It will go to a equilibrium state where the same amount will be traveling from E1. It will traverse to E2 and vice versa, something like that.
Why should vice versa happen?
It will achieve equilibrium, no?
No, if I have, okay, yeah, correct. What will be the equilibrium situation? What should be the ratio of N2 by N1 at equilibrium?
Yeah, I think that was the question, sir. Like, what would be N2 at certain temperature? It will depend on the temperature, I think.
Yes, exactly, right? This ratio will be exponential minus E2 minus E1 divided by KT. Okay. If you have this energy spacing is E2 minus E1, basically this is the Boltzmann distribution, right? If you don't say anything else, you can always figure out how many atoms will be in the ground state, how many atoms will be in the higher excited state, correct? This is how you can compute. If any number of levels, you can compute this. This is the regular Boltzmann distribution. Okay. If you look at this, if let's say this E2 minus E1 is 1 eV, okay? Let's just, for the sake of it, let's call this as 1 eV. Okay. If this is 1 eV and this is room temperature, if you take this situation, what will be N2 minus N1? It will be exponential minus 1 eV divided by KT is how much in eV? 26 MeV, right? Let's call it 25 MeV. Okay. So roughly it will turn out to be exponential minus 40, right? What does it tell us? It tells us that most of the atoms are in the ground state at room temperature for this particular scenario. Agree with me, Ghosh? Okay, good. So most of the atoms are in ground state now. Now, I'm asking you a slightly different problem. I'm saying if N2 at, let's say, tau r, okay, let's again go back. Let me pull this down so that I can, this is a different topic. Let's do this here. This is initially. Now, coming back to this, at N2 equal to T equal to tau r. What is the concentration at of N2? Can someone tell me this? Ritu, what will be the concentration? I have somehow prepared my system in such a way that initially my atoms are all in excited state. Initially, there's nothing else in the ground state, 100 and 0. These are the distribution of atoms. There are 100 atoms in the system. Somehow it is prepared in such a way that all the atoms are in the excited state. Okay. If I shine light of 1 eV photons in this, will it absorb light?
No, sir. I think if if N2 is filled, so there is no question of absorbing. In that case, stimulated emission should happen.
Yes, exactly, right. It should only have stimulated emission can happen. Absorption cannot happen because it's essentially population inversion in some way. Okay, but here let's come back to it. Now, after tau equal to tau radiative time, whatever that is, okay, what do you think will happen to the N2?
N2 divided by T.
N0 of 0 divider into exponential what?
Minus by 2, then T equals 2, so it becomes minus 1.
Yeah. Okay. So roughly 67% of it, no, exponential minus is how much? Minus 1 is roughly 67%, right? So only 67% will remain, right? After this one, 9, most of it will come down, 2 or 3 radiative lifetimes, correct? So this is what happens. Now, if you don't do anything with the system, it's a simple open system where the photons can simply go out, then this is what will happen. But suppose I somehow create a system where I enclose this system in a cavity. I create a cavity which is essentially mirrors, let's say. I don't let the photons escape anywhere else. Somehow I try to confine that in a cavity. And I put let's say this gas containing 100 atoms here. So, I mean, it's a slightly tricky thing, but it can be done. Okay, you can create a situation where you create a cavity. Now, if you do that, or let's say it's somehow some kind of a spherical cavity which is very, very perfectly confining. Okay, if I say mirrors, it might be confusing, but any cavity, okay, cavity confining photons. If I have this scenario, what can happen? The photons that are emitted, right, the 1 eV photons that are emitted, will they be lost? No, they're around in the same place, no? So now there is a possibility that an atom can emit a photon out, and that photon can be reabsorbed, and the atom can go back to upper state. Okay? Agree with me so far? Ghosh? Or did he leave? Oh, you're there. Okay, fine. Okay. Now, the atom can lose this, this cavity can actually help if it's a perfect cavity. Then in principle, after some time, the photon will come back, it will get absorbed, again it will go up and then come, all that. The process can repeat, right? So that is what we call as Rabi oscillations. Okay. So this is a simplest way of understanding it. If I open that picture for you, the assignment, what we are saying is, on the left, we are let's say plotting the probability of electrons or atoms being in the excited state here. Okay, sorry, in the second level. What you see is initially the atoms are all in the ground state, and then they went up to the first excited state, came down to the ground state, again went up to the excited state and ground state, and so on. The atoms can exchange energy with the cavity perfectly in such a way that you keep pushing them up and down. You keep populating excited state. You are essentially preparing the quantum system in a desired state, whether it is excited state or the ground state or something. We can program it to that situation by doing some gimmicks. Okay, that is for an ideal cavity. But suppose your cavity is not ideal. It is going to, some photons are going to leak out, right? It's never going to be ideal all the time. Correct? Now, for that scenario, you have a situation where the number of atoms in excited state oscillates, and after a long time, it sort of becomes flat. There's no more oscillation there, because eventually the number of the photons are getting lost, and then they're not getting reabsorbed. So that process is not very efficient. At some point, it loses. Okay. Now, the third situation is they're completely lost easily, very easily. So you'll never have this oscillation. You just have, at some point, some equilibrium, density of atoms in the excited state and something in the ground state. That can happen. Okay. That is the three situations that can happen. Now, in this assignment, that's what we have asked. Initially, we started with 100 atoms. What is the populations? Then atoms follow Boltzmann statistics at equilibrium. Well, that's the answer here. You can compute what it is. And then you try three different cavities. Now, the question is, which of the following curves represent strong coupling between atoms and optical cavity? Of course, the strong coupling means you are able to exchange energy between the cavity and the atom system. Okay. So that is A and B, wherein you are able to exchange energies. That's why you are seeing these oscillations, which we call as Rabi oscillations. Now, in the question, next one, you shine laser, what happens, and so on. How do we program it? That's a different matter. Now, in question number 5, in curve C, we do not observe any oscillations in the probability of finding atoms in the excited state. This is because the damping rate is much faster. Damping is much faster, okay, than the exchange, the Rabi frequency. Rabi frequency is the amount of, the frequency with which the atoms oscillate from the ground to higher state and back. Okay, there's a certain frequency associated with that. But if you're able to lose photons much faster than this, okay, then you cannot have these oscillations and you have some flat situation like this. So basically, when you have a low Q cavity, your gamma, that is the rate at which you are losing the photons from the cavity, is greater than the frequency at which you are oscillating. Then you see that it's actually not an idea. I mean, it's not conducive for Rabi oscillations. Did I answer the question, Ghosh, or you have any further questions on this?
Sir, here I just want to ask another thing. Like, it is completely correct that you are saying that the gamma has to be greater than omega r. Okay, but as I can understand from the lecture, this curve C, okay, starts from gamma equal to omega r itself.
Means here,
like, yeah,
yes.
C, yes.
I see. Okay.
So actually, the confusion is arising due to that part only. Since for gamma equal to omega r, I am getting that flat curve itself. So there are two obviously the gamma greater than omega r is absolutely correct. There is no question about that. But at gamma equal to omega r itself, we are going to see that curve C, na?
Now, okay, so now I'll have to go back and look at what exactly was the conditions for calculating this. Okay, let me clarify that for you. What exactly was the situation? But I don't right now remember offhand what is the situation. We just picked up some numbers. I'm not certain what the number was. Okay.
Okay, sir, no problem.
Yeah, we will take a look at that. Jiran, do you remember this? What was the numbers of gamma? How much did we choose? Gamma by omega r.
Sir, no, sir, I can't recall it as of now.
Okay.
But actually, sir, like we mentioned the condition, always this omega r means the exchange rate of energy should be larger than the damping rate.
Yes. Yeah. If the damping is faster, then it loses energy and you don't have any, oscillations. That is there. But how much was the numbers? In the textbook, I think we had some in the lectures we had some numbers. Let me open that. This was week 8 or week 7, I believe, right?
It's week 8.
Week 8, okay. It's much before all the fabrication business. Yeah, here. In this case, well, yeah, this is gamma and omega r, right? But in this is around 0.2. In the case we have taken, I think we have changed the number slightly. So we'll have to go back and look at what we did here. Here, if you are saying, if you go back and look at it, basically it depends on how much is the ratio, gamma to omega, the calculations.
Okay, sir. Actually, I was not aware about this fact. Okay.
No, we just basically implemented this and we just saw that, okay, there's a simple expression for this. We will do one thing. Can you shoot an email on the discussion group? We'll answer to that with the code. Okay, so that will make it clear.
Okay.
Okay? Yeah.
Okay, sir.
Please send one email and we'll reply. Yeah. There is another question. No, Vinod, what was that? Other one?
No, I could see only one question, sir.
No. Question 5 and
5 and question 8.
8, okay. Figure referring to figure 4, which is figure 4. Okay, this one, okay. The absorption and emission spectrum of some gain materials are plotted in figure 5. Choose the gain material which is best suitable. Okay, Ghosh, what do you think it is? We just basically made up this. The idea is, the essential idea, no? What we're trying to communicate here is this. Now, first point we want to communicate is, let's say you have these energy levels like this, E1, E2. Okay. We want to emphasize that there's also certain energy, there is a time associated with it. Okay. There's a delta energy associated with it. These are never discrete single lines, right? There's always a certain delta E2 and delta E1 associated with that. Okay. And that's why, another form of uncertainty relation, which sometimes you don't come across, but delta E times delta T is h bar, of the order of h bar. Okay? With me, Ghosh? Hello, Ghosh? Was it okay? With me so far? What we are saying in this case is, if you have a energy spectrum like this, I can draw this spectrum, no? I have tried to draw it like this. Energy versus, let's say, some intensity, something, okay? Normalized intensity or some whatever, arbitrary units. AU, okay? Let's say, we are able to somehow plot the spectrum, okay? Now, I should not call it intensity, but yeah, available states or whatever. Yeah, number of states available, maybe that's easy. Okay. States available. Now, what we are saying is, you have lines like this. These will be the two lines. Let's say this is E2 and this is E1. When I draw a line like this, I'm not really telling you what is the width of that. Okay. There is this width that is associated with this, which I call it as delta E1, and this is delta E2. Okay, when I can draw a spectrum like this. Okay, like for example, when you take a spectrum of a, let's say, sodium lamp, you get these lines, sharp lines, essentially telling you that at that point you have absorption happening and things like that. Okay, so I have somehow managed to figure out what's the spectrum, energy spectrum of this, and I am seeing that there is some delta E given to us. Now, what is suitable for lasing is a question. What is a necessary condition for lasing? In addition to 2 levels, of course, one of the conditions is that the lower level, ideally speaking, you want to have a 4-level system like this: ground state, E0, and then E1, E2, E3. 4-level system is ideal in this scenario. What I'm going to do is, I'll take some pump. I will pump to the higher level. Okay, this is my pump. Now, from the pump state, you will relax very quickly here, non-radiative relaxation. That means it can be thermal, it can be OJ, whatever. Yeah. So I want it to be relaxing here, and then I want to emit a photon here. Photon emission. Photons to be emitted. And of course, finally, they should come back non-radiatively to non-radiative decay to ground state. This is my cycle. Okay. Now, for lasing to be efficient, the higher level should be long-lived, and lower level should be short-lived. What do you mean by that? If the atoms come down to this state, they should quickly de-excite, because I want empty states here available. Okay, and I want full states here. So basically, I'll pump and I'll wait for the electrons to come, atoms to come into this second level, and keep waiting there for a long time. They should not emit photon. That is when when these conditions are met, I'll have maximum population inversion. When I meet these conditions, only then I can have maximum population inversion. So, how do we achieve this condition? When is the lifetime of the state long? When it is very, very narrow. Correct? Delta E should be very, very short, so that this lifetime is roughly tau r, which is how much uncertainty is there that is very long. When delta E is very small. When delta E is very large, then this will be very small. That's the uncertainty. With that, what we gave you was this. Various spectra like this, wherein higher level is 3-1, right? This is sharp. That means it is long-lived. Okay. And lower level is broad. That means it is short-lived. So like that, multiple things we have given and said which is a suitable thing for lasing. Okay. I would say A is more suitable here. Well, why A and B? Sorry, just a minute. Lower level is broad, so this is good. Why are we saying here?
Sir, the x-axis is energy. And
Okay.
so
This is higher level. This is higher
E3
level.
E3 so I formed it in the way that absorption light wind should be broader, so that there is more we can have more excitation of electrons from ground to excited state. And then as you said, then the emission wavelength, because you always have a shift from the absorption spectrum to the emission spectrum, and that's narrow width.
So this is the first one you're talking about, the third one, right? This is the pump.
The B
The
one.
pump should be broad, and then this should be sharp. Yeah, you didn't show the first one. Okay, I was thinking is that it's not the lasing level you're talking about. You're essentially talking about this level. Why is this? Yeah, we are essentially talking about this level and this level.
Yes, sir. Yeah. E2 by E1 should be, for me, it should be narrow, long-lived state.
Yeah, correct. That's what you're given here. E3 and E2, yeah, you're given. So good. Yeah. So you have a 3-level system. Yeah, makes sense. Right? So that's why, yeah, this should be long so that it can absorb nicely, and then wait in this so that it can lace. Yeah. Does that answer your question, Ghosh?
Sir, I do have a question here. See, actually, here the ambiguity is occurring from the hint that has been given in question number 8. Okay. So here, what has been given, that the width of the spectral line is inversely proportional to the lifetime. Okay. So obviously option B is the correct one that I can understand, because for lasing we need a sharp what the correct time forward, the line width should be small. Okay, but as you can see, like in for lasing, for the 3-level system that has been given here, okay, tau 31 is 1 millisecond. Okay. And tau 21 has to be 1 nanosecond, and 32 is 1 picosecond. Okay. So that option is correct. Now for question number 8, if I follow through the hint that has been given here, okay, according to that hint, okay, the 3-1, okay, since 3-1, tau 3-1 is the maximum among these 3 values, okay, that should be 1 by tau 3-1. Okay.
Okay. The
So
basic is not,
we must have the smallest spectral width.
Smallest time. Yeah, tau 3-1 should be smallest time in this case. Yeah, because we want a broad absorption spectrum.
Yeah. So according to the hint, what I felt during doing this assignment, okay, that option A should be the correct one.
No, but here, like tau 3-1 was there in the earlier question, but when we say about absorption, it should be tau 1-3. Right, like we want to excite.
Which is absorption, which is both are.
E31, sir. Like E31 will be the absorption. Generally, absorption happens at higher energy.
Correct.
Because if we don't have population inversion, there is no chance we will have lasing. And for population inversion, definitely 3 to 1, that transition should be very long lived. As what he's saying. It also makes sense. 1 upon 1 millisecond will be the long lived state.
Yeah, logically,
What you're saying, yeah. 3-1.
Because we don't want that direct transition. We want through 2 to 1.
Otherwise, it will go through that first. Why should it come back to this level? Correct. The photon can be excited through de-excite through this itself directly. If you say that this is 0.5 nanoseconds, the photons will actually be emitted in this wavelength, and then they will. Why should they? Well, by then actually they would de-excite now, because 1 picosecond, most of it will de-excite here. Sorry, did I? Let's take the scenario of 3-level system. This is a situation we have. Now this is 1 picosecond. And we say this is 1 millisecond and this is 1 nanosecond. That's the problem given to you, right? Did we say?
Yes,
the same this one did we say here?
I think the confusion is arising because I should have mentioned absorption and emission lifetimes are different like that or something. Generally, absorption is always quick.
In this case, we cannot say that, no, because we will. I mean, if you don't say anything, we will say that tau 1-3 equal to tau 3-1. Why should it be different? Unless I give you that additional information that it should be different.
So like it's valid for 2-level systems. That's why we can never achieve population inversion in 2-level, because absorption and emission are similar.
Exactly. They'll be exactly equal, but here it will not be.
Yeah, that line should have been mentioned to
eliminate indirectly there. It's indirectly there because you have this to be very small, no? your emission cannot be same as absorption. This is absorption lifetime. Let's say tau 1 3, and then emission lifetime is 3 1, right? That will not be equal.
Yes. Yeah, that should have been mentioned so that there would not have been any confusion that
Okay, yeah,
1
that
3 and 3 1 are different.
let's just give it to, I mean, I don't know. We can add that mark if you want, if it's not too late.
Yeah,
For
sure.
week 8 is done.
Sir,
No,
I
right?
think
I
no,
don't
sir,
think-
we
Back
can
1 or 2 weeks back.
Oh,
no, we can put the correction part. We
It's
can
okay.
write to
Okay. Thanks for bringing it to our attention. Yeah.
And sir, that question number 5, sir, I just want to request you, because see, in the class that I followed from the class, that the gamma equal to omega value will also give the flat curve. Okay.
Mhm.
So that's why I made the mistake by while choosing the option. So if you can consider that question also, the both
No,
options.
I would not consider. Well, did you choose E or F?
I choose the last one, the omega gamma equal to omega r, and low Q factor.
Well, I mean, that is not the only question answer for sure, right? Because gamma is greater than that.
Yes, sir. That would be also true, but actually, I just followed the class. That's why
I see.
yeah. Uh,
Let's take a look. Yeah, it's okay.
okay, sir.
Anything? Any other questions, guys? From the forums?
Sir, there was one question like which we missed to answer. Someone asked like, is there some analog to strain in photonic crystals? Analog of strain.
Well, I mean, you could argue that definitely, but see, we have a equivalence between how the photonic lattices behave and electronic lattices behave. In case of electronic lattices, when you have strain, you're essentially changing the mobility. The band curvatures are changing and mobility is changing. Right? In the case of photonics, you can talk, I mean, we have to look at how the bands are and then how these dielectric and air bands, the speed at which the waves propagating that should be there. I suppose there should be something like that for sure. Yeah. Mainly the speed with which the waves propagate will be different. If you change the lattice a little bit, you strain the lattice a little bit, the speed of propagation, because the bands will change, the group velocity will change, and so you have different speed of propagation. That should happen. Any other questions, Jinal?
Yes, sir. Just checking it.
Well, I think there are a lot of questions on. Well, yeah.
Yes, sir. There was one interesting question. Someone asked like why not uncertainty in the EM wave should be in the form of square rather than circle? Because we always show that photon and like the number and phase uncertainty by circle.
Okay.
So why
Why-
it should not be in the form of square?
Well, if you want it to be square, then the equation should be different, right? What is the equation for energy?
And
No. I mean, basically, if you look at it in quadrature terms, right? You're talking
yes,
about quadratures, x1, x2, right? And in terms of quadratures, how will you write the Hamiltonian?
it will be yes, sir. Cos and sine terms
Yeah, cosine
and
times
the
sine.
magnitude. So
Yeah.
it can be
Yeah.
defined by r and theta.
Hamiltonian is basically p square by 2m plus
Oh, yeah.
half m omega x square, right? That's what we are writing.
Yeah.
X square and p square, no. Whenever you have square quadratic equation, you're going to have, and essentially we made it dimensionless. If you don't make it dimensionless and plot it in terms of x and p or something like that, you'll have very, very different shape ellipses you can get. But we choose these dimensionless quantities, x1 and x2, such that they're very equivalent, right? X2 are dimensionless. They're normalized such that there's a dimensionless. And now, effectively, I would say that what is a circle? It is x1 square plus x2 square equal to 1. Right? So in my mind, it makes sense to me that your uncertainty also should be in the circular fashion, not a square, because you're finally coming from quadratic equation like this.
Yes, sir.
Well, I mean, I don't remember the equations exactly right now, but you have x1 plus ix2, right? What is this equal to? Anyway, you have the math, right? If you look at the math carefully, you'll see that this is a coherent state, no? A coherent state, and then what is the energy of it, you can calculate and see what happens. Yeah.
Yes, sir.
For a squeeze state, it is not true, of course, because one of the dimensions we are reducing the uncertainty, so that's why it's an ellipse, not a circle. Yeah. Okay.
Yes, sir.
Other things are all, some you've answered this evanescent waves, and right?
Yes, sir. Then
Interaction Hamiltonian. Well, that is essentially the dipole. Suman, you have any questions?
Sir, hello.
Hello, yeah. You have any questions?
Sir, that question, what you already discussed, but that the tau 1, tau 2, and tau 3, that question, okay, 1 millisecond and hello, okay. So that question,
Yes.
that tower related to means that is stimulated or rather than other, means other kind of tau. That is the for means that tau, that question is means misunderstood by me, I think. But
Okay.
that tau is means for stimulated emission. That tau is for stimulated emission, or for like the another kind of thing.
No, it is basically the lifetime. It is combination of spontaneous stimulation, stimulated emission. It doesn't matter, right? Lifetime is lifetime for a state. Okay.
Okay, so there is no distinguish between.
I think we lost you. Well, if you don't have any other excitation field, it is spontaneous emission. Once you have excitation field, whether it's in phase and so on, it can emit also. The coefficient will be different. The B21 versus A21 factor, right? It depends whether which is stronger.
Okay, sir. Okay. Thank you.
Sadhu Khan,
Yes, sir.
you have any questions?
Sir, actually, it was in a very short notice, so I couldn't go through the whole thing. So,
Okay. I'm really sorry about that. This was.
no, it's okay, sir.
But I'll try to, if you have any questions, let us know. I'll anyway schedule one more time, next week, and next couple of weeks, I'll do it every week. Okay.
Okay, sir.
I will do it, and then we will get back again. Please, feel free to ask us questions, because only when you guys are active, we become active. Otherwise, we are also, it's there already. All the lectures are recorded, assignments are done, so we don't really worry too much. If you ask questions, we'll go back and we'll really try to make it better.
Sir, just one more question. Like in assignment 9, the previous week, which has already been completed. So in the last question, there was a question like in regard to the photo detection process, arrange the following sequence of events chronologically. Yeah. So, like I have just a simple confusion here. That is that first the illumination will happen by the light beam. Okay. So after that, the interaction of the light with the atoms in the detector will happen. Okay. And after that, what will happen is E4. That is liberation of individual electrons by the photoelectric effect. So after that, I had a confusion between E1 and E2. So which one should occur first? Okay, in the electronic process that is going to occur in case of detection. So can you please explain what is happening physically here?
Right. So what we are saying here is by till that part it's okay, no? When it interacts and all that.
Yes,
now
sir.
you get an electron, but that single electron will give you very, very small amount of current. What is current? Number of electrons per unit time, correct? So it is a very, very small number. We have to somehow multiply that. We have to increase the number of electrons by, let's say, if you use an avalanche process, it's called as avalanche photodetector, SPAD we call it, or any other different types of photo multiplier tubes wherein you have cathode and anode, and then you basically accelerate the electron and create cascaded number of more electrons and so on. So you have various processes, because one single electron is a very tiny amount of current, right?
Yes.
I don't even attoamps or something like that, below attoamps kind of current, right? It's very, very small. So we cannot measure that. We'll have too much of noise. So that's why we are saying that we are triggering and then we are releasing more electrons by whatever process. It can be photomultiplier tube or avalanche photodiode or something, whatever. And then finally, once we have more of electrons, then that electrons will flow in the external circuit and it gives a current pulse. That's why we put E2 as the last one.
Okay. Okay, sir. One more question. Like, it might sound very silly. Like, once you have in your class, you have mentioned like that for large number of photons, when we can consider a classical optics, classical theories.
Yes.
Yeah. So, like, I have a question here. For what amount of power, is there any limit, numerical limit or something like that, that up to this P1 amount of power I can consider this phenomena or this kind of theorems we can apply, and above that we can't, like this? Is there any boundaries?
Well, it depends on basically what sort of experiments you're doing. Okay, so now if you look at if I look at a simplistic way of one rule of thumb for me is this. Okay, what is energy quantization of energy in energy of photons? En equal to n plus half h cross omega, right? Correct. This is the quantum picture, correct? The classical picture is En is equal to n h cross omega. This is a classical. If you have n number of photons, the total energy is this much. Classical, right? Now, this is the 0 point energy that is coming because of quantum description, right? 0 point energy. Now, what we are saying is, if your n is large, let's say n equal to 10, my classical and quantum pictures are relatively close, right? How much is error? If you think about it, let's say I'll call this as Q, and this is C, classical. Okay. If I do the error, basically if n equal to 10, delta, whatever, E minus En of quantum minus En of classical divided by En of quantum, let's say. If you do this energy, this is a very small fraction. The amount of error is very small, even if you put 10 photons, right? The 0 point energy is very, very small compared to the total amount of energy in the system. So it's mostly classical after that. Okay, if you have, that's why I would say 1-2 photons, I would say it is quantum. But the moment you go to 10 photons, 100 photons, and effectively it is all just classical description would work. Another way of thinking about it is in terms of the quadratures. This is my x1, this is my x2. How am I representing my number state, whatever, coherent state, let's say? I'll put it as a uncertainty, region of uncertainty here, right? Now, what is this distance?
This is the most probably the number of photons.
Root n, right? Root of n, I think,
Yeah.
right? Of photons. And now this is uncertainty, right? Now, when my uncertainty is much larger than this dimension should be what? 1/4, correct? Delta x1 and delta x2 roughly, right? Delta x1 equal to delta x2 is equal to 1/4 for a coherent state, correct? For a perfect, laser or something like that. Now, when your root n is much larger, n equal to 10, let's say, your uncertainty in this region of uncertainty is very, very small compared to this distance. Then effectively, how your electromagnetic wave, how will you represent it? When you have, let's say, uncertain, let's say n equal to 1, let's assume that n equal to 1 or 2, let's say n equal to 2. Okay? If you have 2 photons, that means your electromagnetic wave, if you want to draw it, there is a certain region of certain uncertainty like this, right? You agree?
Yes,
This
sir.
part?
Yes, sir.
The reason we are representing it by this area is that I don't have a single position, or this is my number and phase uncertainty, right? Delta n, delta phi is greater than 1/4, right? Or something like that, greater than or equal to 1/4 or something. Okay, so the minimum state is equal to 1/4. So now you're saying that you cannot define a voltage at a particular instant of time, but there's an uncertainty in the amplitude and uncertainty in the phase as well. That's what we are saying. Now, when your n is large, let's say n equal to 100 you put, and this is much larger than 1/4, no, the diameter, then you're essentially describing your photon as a wave, single wave like this, one single line. You don't have to worry about the uncertainty effects.
Okay, sir.
Yeah. So even if you go to 10 photons, I would argue that it is classical again. I mean, there's nothing much quantum left there. Okay, or the same energy. You have different energies, a lot of interesting things can happen. Yeah.
Sir, in that case, like in case of nano laser or something like that, where we deal with a very small spectral width or something in terms of the power spectrum and all. So, do such phenomena come into play for such?
Well, I mean, you can have single photon emissions. Yeah. At very, very weak, if you pulse a nano laser or something, you can have single photon emissions. Yes.
Okay, so like if I say like these are very extreme specific cases, so will that I will be very, very much wrong, or it is correct statement? Like these kind of phenomena are specific cases where we encountered this kind of like phase and in relation.
No, these are nowadays you produce them routinely in the labs.
Okay.
See, think of a nanowatt laser, okay? Nanowatt or a picowatt laser. You pulse it, produce 100 picosecond pulse. Effectively, have a single photon there. Or in that you have to attenuate a little bit, but yeah, you can quickly get to a point where you're talking of single photons.
Okay, sir.
Yeah. By the way, what is your background? What are you doing right now?
I am doing research in photonics.
Where?
In IIT Jodhpur.
IIT Jodhpur. Okay, all right. With whom?
Yeah, Dr. Somnath Ghosh.
Okay, all right. All right. Yeah. I hope that clarified, yeah?
Yeah. Thank you, sir.
Thank you. Yeah. Anything else?
Sir, there is a question on YouTube. So he is Venkat Karthik. What is one photon? What is one
photon? Okay, I think let me give you a funny answer, I guess. One second. Well, this is one. I mean, this is one form of, I don't know exactly what is the real thing, but every physicist thinks that he knows what a photon is. I spent my life to find out what a photon is, and I still don't know what it is. Or there's another variant of it, wherein I think we say that, it's much more, every fool thinks that he understands what a photon is, but half a century of conscious brooding has not given me what a photon is. One way of looking at it. Just fun aside, what we mean by that is, photon in some sense is a quantum of energy, a packet of energy, which is emitted whenever an electron makes a transition between two states. Let's say that's a photon. Right? The amount of energy dictates what its frequency is and so on. So that is a photon. Now, usually you'll never have a situation where a single quantum of energy is required, because if you take, let's say, 624 nanometer light or something like that, the energy is roughly 2 eV. 2 eV means 2 into 1.602 into e power minus 19 joules. Very, very small amount of energy it is. Okay, a single photon's energy is minuscule. Okay, very small. That's why we use electron volts, not joules. So it is, if you look at light, like for example, or take a laser pointer, it has about 10 power 15 photons per second. So large flux of photons that are coming out of the laser. So for you to visibly see it, you need a large number of photons. For example, our eyes are sensitive to down to about 6 to 7 photons. In appropriate conditions, apparently the human eye can detect even 6-7 photons. It cannot detect single photons. It can at least 6 to 7 photons are there. It will know it. There will be an electrical signal that is sent in your brain, especially if you're in a dark room conditioned very, very well, then you can detect that level. That's the kind of a dynamic range that your eyes have. Actually, you can detect millions and billions of photons down to single, 10 photons. So that's something that amazing photodetector anyway, I guess. Okay. So one way of looking at it is a photon is a quantum of energy. That works in most of the cases, right? I hope I answered it, or anybody else has a better answer than this. Jinal, Vinod, or Saurabh, any of you have a better answer than this? Did I answer the question, Vinod? I mean, the guy is okay with it, or he has a follow-up or something?
We need to wait, sir.
Achha, because there's a lag.
Yeah, there will be a small delay.
Yeah.
He has seen the quote because he gave some smiley symbol.
I see. Good. No, that's actually, my professor used to put that quote in the introduction to the course. 50 years of, shall I erase this course? Anyway, good. All right. Any other questions, guys? Well, Suman, Ghosh, Sadhu Khan, thank you so much for joining. We really appreciate you taking your time out. Any questions are there, please feel free to write to us and we'll be happy to answer. All right. If nothing else, we'll stop. Yeah. We'll come back again next week around the same time. Okay. Okay, guys. So the IIT Madras team, if you're okay, we can close this. Moderator, can we close it? By the way, my voice was clear because I'm speaking slightly far away from the...
No, sir. Clear.
Okay, fine. Great. Moderator, can we close this? If not, let's sign out, guys. I mean, it's okay.
Okay.
All right. Thank you so much, everyone. Have a good night.
Yes.